I think we can start. Mina, are you okay with?
Yeah, sounds great.
Okay. So we are very happy to have today with us Mina Aganagic from Berkeley, and she will tell us about node categorification from mirror symmetry. So Mina, just do you prefer the questions to be at the end or during the talk?
During the talk is just fine.
Okay. So please either ask questions in the chat or just unmute yourself and ask whatever bothers you. Thank you.
Great.
So, Mina, take it.
All right. So thanks for inviting me. It's as I said, it's a pleasure and honor to be here. So I'll tell you about the work that appeared in two papers listed here and also a little bit beyond. Let's see if I can. So in '98, Coulomb showed that there's a deeper structure that underlies a link invariant discovered by Jones in '85. Jones associated to a link a polynomial in one variable, Q, such that links with different polynomials cannot be smoothly deformed into each other. And the coefficients turned out to always be integer. Coulomb explained that one can recover the Jones polynomial as a shadow of a cohomology theory, which to link associates a collection of vector spaces graded by, which are bigraded, graded by a fermion number and another equivariant grading that keeps track of Q. The vector spaces are themselves link invariants, and the equivariant Euler characteristic is the Jones polynomial. Edward Witten explained in '88 that Jones polynomial comes from Chern-Simons theory with gauge group based on Lie algebra SU2 with effective Chern-Simons level related to Q. Jones, from this perspective, Jones polynomial is the expectation value of a collection of Wilson loops in the fundamental representation of SU2 supported along link components in Chern-Simons theory in R3. This immediately leads to the generalization of the Jones polynomial by varying the Lie algebras and the representations. The resulting invariants are known as quantum group invariants. The relation of Witten's invariants to quantum groups was developed by Reshetikhin and Derived a year later. I'll explain that Coulomb's construction also has an origin in physics and one that generalizes to all gauge groups in parallel to what Witten did in '88. From string theory, one derives, in fact, two approaches related by a version of two-dimensional mirror symmetry. The reason two-dimensional physics enters is that descriptions we will get come from two-dimensional theories associated to a link times time in R3 times time. In fact, string theory gives us a bit more. The theory turns out to naturally be equipped to describe arbitrary links in R2 times S1 and not just R3. The two-dimensional theories come from two-dimensional defects of the six-dimensional 0-2 conformal field theory, as anticipated in the works of Oguria and Waffa and Gukov, Schwartz, and Waffa. The implication of their works was that if one was able to understand how to extract the spaces of BPS states from 0-2 theory with defects, they will be covenant homology groups and their generalizations. There is a six-dimensional or five-dimensional approach to the problem that's being developed by Witten. The two approaches I'll describe are complementary, and they solve the problem from perspective of two-dimensional theories on defects themselves. The first approach is in a spirit similar to that of Kamnitzer and Kautis. Recently, Ben Webster proved that this approach is equivalent to his early approach based on KRLW algebras, and in fact, generalizes them to invariants of knots in R2 times S1. The main subject of the talk is the second approach. The second approach will also turn out to have an algebraic description by a version of KRLW algebra, but much simpler. The relation between two approaches is what I call equivariant homological mirror symmetry. The equivariant homological mirror symmetry isn't an equivalence of categories, but rather a correspondence of objects and morphisms between them. The reason transhumance invariants of knots are interesting and is, from my perspective, not so much that one cares about knots and the invariants, but rather because of the wealth of math and physics connections you get to discover once you understand them. The fact that this structure arises from a deeper theory will surely lead to many more connections. We'll see one of them here, two solvable but highly non-trivial examples of homological mirror symmetry that connected to representation theory. In the same 89 paper, Witten showed that underlying transhumance theory is a two-dimensional conformal field theory, the WZW model with affine Lie algebra symmetry. We'll take this as the starting point. The Hilbert space of transhumance theory is the space of conformal blocks of the affine Lie algebra on a Riemann surface, where a Wilson line puncturing the Riemann surface translate to insertions of vertex operators. By varying positions of vertex operators on the Riemann surface as a function of transhumance time, we get a colored braid in three-dimensional space. The transhumance path integral computes a matrix that takes the Hilbert space and the space of conformal blocks from one time slice to another along the path corresponding to the braid. Any link can be represented as any link invariant can be represented as a matrix element of such a braiding matrix between pairs of conformal blocks that correspond to caps and cups. Some specific conformal blocks. The state that describes caps and cups correspond to conformal blocks in which pairs of vertex operators colored by complex conjugate representations come together and fuse to disappear. So both braiding and fusion of conformal field theory play an important role in the story. The braiding matrices and fusion matrices are known explicitly. To find them, one wants to think about conformal blocks as solutions to a differential equation. The equation is the one that is discovered by Knizhnik and Homological. More precisely, the trigonometric version of it, because we're working on a Riemann surface, which is an infinite cylinder as opposed to a plane. But from perspective of the KZ equation, the braiding matrix is simply the monodromy matrix that takes along the path and parameter space described by the braid. The monodromy problem for the KZ equation was solved by Drinfeld in '89 and by Cousin and Lustig, following earlier works of Tsuchiya, Kanye, and Kono for SU2. They showed that monodromy matrix that reorders a neighboring pair of vertex operators is the R matrix of the quantum group corresponding to G, whose construction is canonical. Now, our starting point for categorification of link invariants is the realization of conformal blocks, which comes from quantum field theory in 2 dimensions with n equals to 2 supersymmetry, and which in turn originates from string theory. The KZ equation and the conformal blocks corresponding to it have a striking and much more rigid generalization whose existence is explained by string theory. The specific deformation is discovered by Igor Frankl and Nikolai Reshetikhin in the 80s, who showed that one can break conformal invariants of the affine Lie algebra while preserving much of the structure provided by conformal field theory. So we'll take the Riemann surface where conformal blocks live to be a punctured infinite cylinder rather than a plane. Because we'll be breaking conformal invariants, the two are no longer equivalent. The deformation is based on replacing the affine Lie algebra by what they call quantum affine algebra, which is its one parameter deformation. The parameter we'll call h bar. This replaces the KZ equation by the quantum Knizhnik's homological equation, or QKZ equation, which is a difference equation. We'll recover the KZ equation from the QKZ equation in a limit in which the step of the difference equation and the parameter h bar go to 1, keeping the level kappa fixed. So the limit keeps fixed positions of vertex operators on the Riemann surface. Like in conformal case, solutions of the QKZ equation can be obtained as correlators of chiral vertex operators, except that everything is Q deformed. So we'll call the solutions of QKZ equation you get in this way Q conformal blocks of the quantum affine algebra. So string theory, which they originate from, is the 2,0 little string theory in 6 dimensions, labeled by simply laced Lie algebra G. One gets this little string theory as a limit of type 2B string theory on an AD singularity in a limit where one decouples the 10-dimensional bulk and keeps the 6-dimensional physics. String physics. So we are simply taking G string to 0, keeping M string fixed. So from now on, we'll take the Lie algebra to be simply laced. There is a generalization to non-simply laced Lie algebras, but it involves extra steps. So we'll want to study the 2,0 little string theory on a background, which is a product of the Riemann surface, where conformal blocks live, of D, which is the domain of 2-dimensional theories that will play the key role in the story, and an extra complex plane. The vertex operators on the Riemann surface come from a collection of defects in little string theory, which are inherited from D-branes of 10-dimensional string. The D-branes you need for this are D3 branes originate from D3 branes of type 2B string theory. So they lead to 2-dimensional defects of the 6-dimensional theory that are supported on D and at points on this extra complex plane and at points on the Riemann surface. We'll need 2 different kinds of D-branes. The D-branes that leads, firstly, the theory on the D3 branes is by works of Douglas and Moore, described by a quiver gauge theory of AD type. The D-branes that lead to vertex operators are associated to flavor nodes of the quiver. And we'll need an additional D-branes associated with gauge group nodes as well. The theory on D-branes supported on this 2-dimensional sub-manifold of 6-dimensional 2-0 theory. It turns out to be a 3-dimensional gauge theory on D times S1 rather than simply a 2-dimensional gauge theory on D. This is simply because space transfers to the D-branes involves a compact circle. So one has string winding modes. One has to sum over string winding modes, or equivalently, you have to T-dualize. Now, one of the results of my prior work with Okunkov is that one can get the fundamental solution to the QKZ equation, which spans the space of conformal blocks of the quantum affine algebra from either the Coulomb branch or the Higgs branch of the 3D gauge theory. The Q conformal blocks arise as supersymmetric partition functions of the 3D theory, 3D n equals to 4 theory on D times S1, which include holonomies for the U1 times U1 R symmetries. And you want to think of D as this very long cigar. The ranks of the vector spaces, which quiver gauge theory should you study, determine the representation and the weight in that representation, which the conformal blocks transform in. So the flavor nodes determine the representation, and then which weight in that representation is determined by the gauge group nodes. The positions of vertex operators are simply positions of heavy flavor D3 branes on the Riemann surface. The highest weight vector of the Raman module is the phi Lioperth parameter of the 3D theory. It comes from a complex scalar field in 2-0 theory, which abelianizes it, or scalar fields for genealogy. Now, the fact that the bulk 2-0 string theory has background complex scalar fields turned on means that the theory lives in a broken phase. And that's important because it implies that all the complicated bulk dynamics isn't important. Which solution of the QKZ?
What do you mean by broken phase? Do you mean
the theory is abelianized. Okay.
So it's like a Coulomb phase.
It's like a Coulomb phase. That's right. Which solution of the QKZ equation the partition function computes depends on the choice of boundary condition at infinity of this long cigar. The fact that one can obtain the partition functions from either the Coulomb branch, which we call X, or X checks the Higgs branch, is a reflection of three-dimensional mirror symmetry, which exchanges X and X check with suitable identifications of parameters and boundary conditions. Now, pursuing the story further, rather than discovering knot invariants, we would discover integrable lattice models. And those in some sense, of a very general kind, associated to elliptic quantum groups. So this is a story developed in the work with Andrei Okunko. Now, we'll rather return to our main interest, which is to obtain superstring realization of conformal blocks of the affine Lie algebra. The conformal limit of, or point particle limit of little string theory, in which it becomes the six-dimensional 0-2 conformal field theory, coincides with the conformal limit of the quantum affine algebra, in which it becomes affine Lie algebra. In the point particle limit, the winding modes that made defects three-dimensional instead of two-dimensional become infinitely heavy. So as a result, in the conformal limit, the theory on defects becomes simply a two-dimensional theory on D. Now, it's surprising, but it's well understood that there are different two-dimensional limits a three-dimensional gauge theory can have. Depends what you keep fixed in the two-dimensional limit. So the point particle limit of little string theory specifies which two-dimensional limit of the three-dimensional gauge theory in a circle we need to take. This is also the limit in which the QKZ equation becomes the KZ equation. So the limit we need turns out not to be the one that takes the three-dimensional gauge theory to a two-dimensional gauge theory with the same Lagrangian. Rather, it's a limit that would do this for the mirror theory, 3D mirror theory. So the resulting theory describes two-dimensional defects of 0-2 conformal field theory, and it's not a gauge theory. So one description of the theory on the defects is a supersymmetric sigma model with a hyperkähler target, which was the Coulomb branch of 3D theory. The Coulomb branch can be described as the moduli space of singular G monopoles with prescribed Dirac singularities on R3, where G here is a Lie group of adjoint type with Lie algebra little g. The Coulomb branch is also a resolution of a certain transversal slice in the affine Grassmannian of G, the same G as for the monopoles. These affine slices in affine Grassmannian play an important role in geometric Langlands correspondence, and this affine Grassmannian description comes about by thinking about moduli space of monopoles on R3 in terms of sequences of Hecke correspondences of G bundles on C, as explained by Kapustin and Witten. Anyhow, so supersymmetry is broken to n equals to 2 by rotations of the transverse complex plane in six-dimensional space. The rotation of this transverse complex plane acts on scalars and vector multiplets of our original 3D theory, and acts by scaling of the holomorphic symplectic form on the Coulomb branch with parameter Q. The symmetry is part of a larger torus of symmetries acting on the Coulomb branch that include whose equivariant parameters include phi Laplace parameters of the original 3D theory. And we'll want to use this full large torus of symmetries. Now, from perspective of the Coulomb branch, X, conformal blocks are partition functions of the supersymmetric sigma model in D, deformed by twisted masses associated to the torus of T. So one has in the interior A-type twist, and at the infinity of this very long cigar, one places a B-type boundary condition. Because the cigar has infinite length, A-type supersymmetry in the interior is compatible with any supersymmetry on the boundary, even of B-type. From perspective of X, KZ equation is what's called a quantum differential equation. It's an equation for flat sections of a connection on a vector bundle with fibers, the homology groups, over the complexified Caylor moduli that was introduced by Giventhal. The fact that the two equations coincide, the KZ equation and the quantum differential equation for our X, or for the Coulomb branch, is a recent theorem of Ivan Danilenko, who's a postdoc at Berkeley. One gets different solutions to the quantum differential equation and the KZ equation by choosing different B-type branes as boundary conditions at infinity. These boundary conditions form a category, and the category of boundary conditions of the sigma model on X, preserving B-type supersymmetry and working equivariantly with respect to T, is known as the derived category of T-equivalent coherent sheaves, as was explained in the works of Douglas, Aspinwall, Horry, and others. Because the KZ equation is the quantum differential equation of X, action of braiding on the space of conformal blocks is the monodromy of the quantum differential equation along a path in complexified Caylor moduli corresponding to the braid. Braid group acts by autoequivalences of the derived category because along a path in Caylor moduli, category of B-type brane stays the same, while the individual branes transform. So it follows that a path integral of the sigma model, where time runs along the annulus, computes the matrix element of monodromy between pairs of conformal blocks corresponding to the chosen B-type branes at the boundary. And the same path integral, if you think of time as running around the circle of the annulus, computes the index of the supercharged Q preserved by the two branes. The cohomology of the supercharged Q is the space of supersymmetric ground states. It's computed by the derived category as its most basic ingredients, the space of morphisms between the pair of branes. So far we understood that B-type branes, the category of B-type branes on X, manifestly categorifies braiding matrix elements between pairs of conformal blocks. The quantum link invariants should also be categorified by the category of B branes on X, because they can also be expressed as matrix elements of the braiding matrix between pairs of conformal blocks. Now, for this, you need to find objects of the derived category whose partition functions are conformal blocks, in which pairs of vertex operators fuse to trivial representation. Now, with help of mirror symmetry, I show that in the first paper that along with braiding, fusion has a geometric interpretation in terms of existence of certain perverse filtrations on the category of B-type branes. These perverse filtrations were envisioned by Chuang and Roquet as a ways of describing the structure needed to describe derived equivalences that come from variations of stability conditions, of Bridgeland stability conditions. But they didn't have many examples of geometric origin. Now, so this provides them. From this, one learns that the branes that lead to caps and cups are not some abstract objects of the derived category. Rather, they are structure sheaves of vanishing cycles in X, simply branes wrapping vanishing cycles. The cycles that shrink to points as vertex operators come together in pairs. These cycles that we need turn out to be simply products of Grassmannians. Anyway, so using very special properties of these perverse filtrations and the vanishing cycle brains, it's not hard to prove that not only do homology groups manifestly categorify quantum link invariants, which they do, but rather, which is manifest from everything we've said so far, but rather that they are themselves link invariants. Ordinarily proving such things is very, very difficult, as for example, works of Kamnitzer and Kautis show. But the virtue of these perverse filtrations is that proofs dramatically simplified. Okay, so in a sense, the reason the statement becomes true, in other words, that the homology groups are link invariants, follows very closely from the fact that you get link invariants from braiding from matrix elements of the braiding matrix in conformal field theory. Conformal field theory makes it manifest that you get a braid invariant, but it's not manifest that you get link invariant. You have to prove that. It relies on properties of fusion and braiding matrices. Anyway, so the theory you get also gives very precise predictions of what the nature is of the underlying perverse equivalences, which one can check in some examples where mathematicians have already computed in, like cotangent bundles of Grassmannians, for example. But in other cases, it's completely new. So recently, Van Webster proved that link invariants that come from X in the way I described are equivalent to the invariants he himself defined in 2013 using KRLW algebras studied by Kovanov and Lauda, by Roquin himself, and in fact generalized them to links in R2 times S1.
Yeah, could you clarify what is the capital calligraphic U?
It's the actual object of the derived category. The brain that corresponds to caps.
It's a B-type boundary condition?
Yes, it's a specific brain, which you should think of as the brains wrapping these vanishing cycles.
But there could be many different vanishing cycles. There's a distinguished.
They're very distinguished vanishing cycles that you get. That's right. Which I spelled out in complete generality in the paper. I should say one restriction of the story, which I swept under the rug here, is that for the space to be smooth, you want representations coloring the knots to be minuscule. Okay. So that's the subset of the fundamental representations. All fundamental representations of SUN, for example, are minuscule. But in general, it's a constraint, which one may be able to relax, but it will definitely require a lot more work, and it might be very difficult. Now, so for the rest of the story, well, as stated, neither the approach by KRLW algebras nor by coherent sheaves on the Coulomb branch is very computation friendly. In the rest of the talk, I want to describe how physics lets you reformulate the problem and solve the theory. This resulting description is completely new. The conformal limit turns out to be not a geometric limit from perspective of the Higgs branch. The limit makes the Higgs branch badly singular because it turns off its scalar variables. What you get instead is a Landau-Gisbert model whose target is roughly speaking an open subset of symmetric products of copies of the Riemann surface visible in type 2b string, the Riemann surface where conformal blocks live, with a potential W, which you derive from 3D from the 3D theory, and taking the limit from the one loop effective superpotential of the 3D theory and taking the limit. Now, the relation between the original space X, the Coulomb branch, and this new space Y is a cousin of ordinary two-dimensional mirror symmetry. The mirror symmetry that relates them isn't an ordinary mirror symmetry because Y turns out to be half the dimension of the Coulomb branch. So what happens instead is that the Coulomb branch has what I call a core locus, which is half-dimensional and contains all the information about its geometry, whose mirror is the target of the Lambda-Gisbert model. This core is simply a locus in the Coulomb branch where complex scalars and vector multiplets, which are massive due to this equivariant parameters that scale the holomorphic symplectic form and which introduce Q in the first place, or the come from rotations of this transverse complex plane, are set to 0. So it's a very natural thing to do. Now, on general grounds, by the origin in the 3D theory, X and Y are related by T-duality or mirror symmetry. Well, these grounds are not that general. This was explained in the connection between the 3D theories and the 2D theories that imply that X and Y are related by mirror symmetry was explained in my work with Hori, Tong, and Kart, relating 3D and 2D in the first place. So anyway, but here we have really a pair of mirror symmetries. You can study the original Coulomb branch, big X, original Coulomb branch, or its mirror, or you can study the core of the Coulomb branch and its mirror. So now we have a pair of X's and a pair of Y's. To distinguish them, I'll call the original Coulomb branch the big X. I'll call its core the small x, because it's half the dimension of the big X. And I'll call the mirror of the big X the big Y, and the mirror of the small x the small y. So anyhow, and yes.
How much supersymmetry we have at this moment?
We have n equals to 2.
N equals to 2.
That's right. So we'll call the small y the equivariant mirror of the big X. Okay, so this relation going diagonally.
Mina, I'm confused about something. Is capital calligraphic X a Higgs bundle moduli space or not?
The capital X is the Coulomb branch.
So that's going to be a Higgs bundle moduli space, right?
Well, I gave.
You described it differently in terms.
I described it in terms of moduli space of monopoles, right?
Yeah, right. But I mean, still, it's also Higgs branch. And the reason I'm asking is, can I think of capital X as a Hitchin system or something like that? Or an opair or a. You said it sounded like a little more like the nilpotent cone. In some cases, these will be important cones. It's an important cone of something, but it's just a Coulomb branch. So it is literally the Coulomb branch of the 3D gauge theory, and the nilpotent cone descriptions are, when they exist, I guess they also follow from works of Gayota and Witten. Okay. I don't know if you have others. They might be. Okay. But what I'll be advocating here is that a much better description is actually in terms of the downstairs theory anyhow. Okay. So the core, the small x, embeds into the big X as a holomorphic Lagrangian of half the dimension. And the big Y, the ordinary mirror of the big X, fibers of the small y with holomorphic Lagrangian C star fibers. Now, since this is new, it's helpful to have an example. So a model example for us will be big X, which is a resolution of the A-1 surface, which is the Coulomb branch of 3D gauge theory with this quiver, and corresponds to Lie algebra SU2. Okay, it's also a moduli space of one smooth SO3 monopole in presence of M singular ones. Anyway, for that X, which is just A-1 surface resolution of it, its core looks like a collection of m-1 p1s with a pair of infinite disks attached. Its ordinary mirror of the big X is, which is this resolution of the am-1 surface, is the big Y, which is what's called the multiplicative am-1 surface with a potential which we won't need. The mirror big Y also has a direct description in terms of either moduli space of monopoles on R2 times S1, which is the multiplicative piece of it, or it's as a moduli space as a Coulomb branch of a 4-dimensional gauge theory in a circle. Anyway, but we will not need that description. So what's important is that this multiplicative big or the big Y is a C star fibration over small y, which is an infinite cylinder with m marked points in the interior. And at the marked points, the C star fibers of the big Y over small degenerate. So in the big Y, there are m-1 Lagrangian spheres, which are mirrored to m-1 vanishing p1s in the big X. And they project to Lagrangians in the small y, which is begin and then the punctures. So this is a familiar picture. Now, in this case, Y is a single copy of the Riemann surface where conformal blocks live. And the marked points are positions of vertex operators, and also places where the C star fibration degenerates. Now, by SYZ mirror symmetry, the small x and the small y, which are mirror pair, share a common base, which in this case is simply a real line with m marked points. The fibers of that base are holonomies of the 3D gauge fields from the 3D theory perspective, are holonomies of the 3D gauge fields around the S1 in the case of Y, and the dual photons in the case of X. And this is sort of a fast way to see why you expect these to be related by 2-dimensional mirror symmetry. More generally, the equivariant mirror of the big X and the ordinary mirror of its core is Y, which is a symmetric product of copies of the Riemann surface where conformal blocks live, with some locus deleted and some singularities resolved. The potential W is a multi-valued holomorphic function on Y. The W0 part of it originates from integrating out charged matter fields in 3 dimensions. The other parts are come from simplified Laplace terms. They're classical from 3-dimensional perspective. And these together they mirror the equivariant action on the big X. In particular, once you turn off the equivariant parameters, the potential just vanishes. Okay. Now, mirror symmetry predicts that conformal blocks of the affine Lie algebra are partition functions of the B-twisted theory on a very long cigar with A-type boundary condition at infinity corresponding to a Lagrangian in the target Y. Now, such amplitudes have the following form, where omega is a...
Mina, is W naught just a sum of the logarithms of differences of the position?
Yes. It's the W0 is you just compute the 3-dimensional effective superpotential, which involves logarithms, and then take a conformal limit. Yes, but that's right. So on general grounds, these amplitudes have the following form, where omega is a top holomorphic form on Y, W is the superpotential, and then there are some insertions of Caudal ring operators. So conformal blocks of the affine Lie algebras, well, that arise in this way are in fact generalizations of pi stability central charge of rings. The generalization is by inserting vertex operators and working equivariantly, which turns on a superpotential. So what we've rediscovered here from mirror symmetry is integral formulation of conformal blocks of the affine Lie algebra, which goes back to works of Fagin and Frankel and Shefman and Varchenko. Actually, there's a little bit more to say here, which is that in general, to get the B model amplitudes to be of such simple form requires knowing what are called the flat coordinates on the parameter space of the Lagrangian model. Construction of these flat coordinates is a very difficult problem in general. One way of saying what they are is simply those are the coordinates in which the A and the B model amplitudes coincide. And for us, the flat coordinates simply are the insertions of vertex operators. Now, there's a reconstruction theory due to Giventhal and Telemann, which says that starting with a solution of quantum differential equation, one gets to reconstruct all genus topological string amplitudes of any semi-simple 2D field theory, any massive two-dimensional field theory. So the B-twisted Lambda-Gisborg model and the A-twisted sigma model on the big X working equivariantly with respect to T are equivalent to all genus. So the closed topological string doesn't know the difference between, doesn't know the dimension, I guess. Now, corresponding to a solution of the KZ equation is an A brane at the boundary of this long cigar at infinity. This brane is an object of the category of A branes, which is a derived Foucault-Seidel category of Y with potential W. The set one needs to delete from the small y, this F naught, gives rise to a collection of one forms on Y with integer periods, which are responsible for equivariant gradings of both the branes and the humps between them. More precisely, the deleting F0 is what lets you define W0. The others associated with phi opposed parameters, other one forms associated with phi with the rest of torus symmetries, not with Q, are there simply because you're working on a cylinder and not on a plane. Now, mirror symmetry helps us understand exactly which questions we need to ask to recover homological not invariance from the small y instead of from the big X. We know already what to ask for big X. The question is what to do on the small y. Now, because the small y is ordinary mirror of the small x, we should start by understanding how to recover homological invariance from the small x instead of the big X. Because the small x is a holomorphic Lagrangian in the big X, recovering invariance from downstairs instead of the upstairs is not trivial. However, there's a canonical way to do it. For every B-type brane on the big X that's relevant for us, comes from a B-type brane on the small x via a functor that simply interprets a brane downstairs as a brane on the bigger space. This functor has what's called an adjoint, which goes the other way from the big X to the small x, so what it does, it takes a B-type brane on the big X to a brane on the small x by tensoring with a structure sheaf and restricting. And the construction of this functor is standard as well. The fact that what adjoint is what lets us relate computations of homes upstairs to those downstairs. What the adjointness means is that for any pair of branes on the big X that come from the small x, the homes between them, so any pair of branes that look like this, the homes between them computed upstairs agree with the homes downstairs, provided you do something slightly surprising. You don't simply compare homes upstairs to downstairs. You instead take the home between one of the branes you need from downstairs, you need to take it up and then send it back down. And this functor that takes the brane up and then sends it back down is not identity. It's a non-trivial thing. So by mirror symmetry, for every pair of B-type branes on the big X that come from the small x, there's a pair of mirror A branes such that the homes on Y, on the small y, agree with those on the big X. the correspondence between these branes and the homes between them is the definition of equivariant homological mirror symmetry. Now, the functors that enter here on the A brane side relates objects downstairs on the small y to branes upstairs on the big Y in the way what mirrors to what happens on the B side. Now, recall our example of the small y, which was equivariant mirror of the big X, which was the AN surface. So mirror to ith vanishing P1 in the small x is a Lagrangian, is a simple interval brane in the small y. The functor that goes up simply amounts to pairing a brane downstairs with a circle fibered over it, which is how you get this picture. The functor that goes down doesn't send a vanishing sphere in the big Y to back to an interval brane on the small y. Instead, computing it either from mirror symmetry or by its definition from Lagrangian correspondences, you find a figure-8 Lagrangian. Now, the basic pair of the basic virtue of these adjoint functors that they preserve the homes are not difficult to see in this case. So the computing homes upstairs on the big Y and downstairs is the same. So, for example, well, in the A model, computing homes, at least the starting point of it is computing intersections of branes. And it's not difficult to see that this is designed precisely so that the homes upstairs and downstairs agree. Now, this example is relevant for covenant homology. For a link obtained by closing a braid with 2D strands for some D, and any link can be represented that way, the corresponding, for some D, corresponding big X is a Coulomb branch of the gauge theory with the same quiver that we had so far, with, but where the rank of the gauge node is D, and the rank of the flavored node is twice D. So this big X is the moduli space of D smooth SO3 monopoles in presence of M singular ones on R3. Now, a helpful fact is that the same big
smooth monopoles on R2 times S1, is that correct?
R3, sorry?
Or on R3.
R3. R3. For the mirror, you only need monopoles on R2 times S1, but for the big X, you don't. For the mirror of big X, you need monopoles on R2 times S1. Okay. Now, it's to motivate us. It's helpful to recall that X, which is a Coulomb, big X, which is a Coulomb branch of the 3D gauge theory, can also be described as an open subspace of a default symmetric product of copies of the A-1 surface via a theorem of Manolescu. And actually, Greg, yes, now it's the way you prove this, which is, well, one way you prove it is described in a nice paper by Richard Thomas. And in fact, yeah, that does use a relation with Hitchin systems. Now, in the big X, the branes that close up the strands are simply branes supported in a vanishing cycle, which turns out to be a product of D non-intersecting P1. So for each cap, you get a P1. Okay, and you need to take a product of them, as many as you have caps, which is D. It's in the equivariant mirror is roughly the open subset of symmetric product corresponding to a configuration of D unordered points on the Riemann surface where conformal blocks live with this potential. By equivariant mirror symmetry, the D cups are products of D non-intersecting figure 8 Lagrangians, and D cups are simply D interval branes. In the Lambda-Gisberg description, both the Lagrangians and the action of braiding on them is geometric. So in fact, we can simply start with a projection of a link to the Riemann surface A, and translate it to a pair of Lagrangians by choosing a bicoloring of an equal number of segments of each color, such that with the rule that red always underpasses the blue. The mirror Lagrangians is simply obtained by simply replacing all the blue segments by figure 8 and all the blue segments by simple intervals and red segments by figure 8s. And the homological link invariant is the space of supersymmetric ground states between the pair of branes you get in this way. The space of supersymmetric ground states can be computed by Floer theory, which is modeled by Morse theory after Morse theory approach to supersymmetric quantum mechanics. You start with the space of perturbative supersymmetric ground states, which is spanned by intersection points of the two Lagrangians and graded by the fermion or Maslov index and by the equivariant degrees. The action of the supercharge on the space is generated by instantons and squares to 0 in absence of anomalies. The cohomology of the resulting complex is the space of exact ground states and the space of morphisms between the branes. Now, in the Floer approach to the A model, the coefficient of the action of the differential is obtained by counting homomorphic disk instantons in Y that interpolate from one intersection point to another of fermion number 1 and of equivariant degree 0. The equivariant degree has to be 0 simply for the disk to be in Y. Now, this theory can be described explicitly thanks to the fact that it's a close cousin of Heegert-Floer theory. We'd get Heegert-Floer theory, a theory that mathematicians developed over last 20 years. We would get Heegert-Floer theory by replacing SU2 by GL1/1. And it leads to Alexander polynomial rather than to the Jones polynomial. The Heegert-Floer theory has a target, which is a different open subset of the symmetric product of D copies of the Riemann surface A with a similar but different potential. It would arise from type 2B string theory on a confold rather than an A1 singularity. And it also has a 3D gauge theory origin, but it would start with a 3D n equals to 2 theory, a theory where deforming the A1 surface to a conifold corresponds to turning on a complex mass for the adjoints in the vector multiplets, in the n equals to 4 vector multiplets. So the description of this long, the differences can be accounted for by thinking of a Heegert-Floer theory associated to GL1/1 as a theory of fermions on the Riemann surface A, while for SU2 or other groups you get anyons. Lagrangians on Y. So since Y is a symmetric product of D copies of the Riemann surface, Lagrangians on Y are simply products of D one-dimensional Lagrangians on the Riemann surface A, and the intersection points between them are simply D tuples of intersection points of one-dimensional Lagrangians taken up to permutations. So again, a holomorphic map from a disk to Y projects with non-negative multiplicities to domains on the Riemann surface A with boundaries of one-dimensional Lagrangians and vertices at their intersection points. So as in Hager-Floer theory, you can read off from this domain the Fermi number and equivariant degree of the map to Y. So for example, the Fermi number or Maslov index of a disk is simply twice what's called the Euler measure related to of the domain, which is the Euler characteristic of the domain with corrections coming from the vertices. So this kind of disk would has Maslov index 1. The index of the supercharged Q in the theory on the interval simply counts the intersection points of Lagrangians, keeping track of all the gradings, the Euler characteristic. Now, the fact that the Euler characteristic of the theory, the sign count of intersection points between these figure eights and straight line branes categorifies the Jones polynomial is in fact a theorem by a mathematician named Bigelow from the 90s, who observed that there's such a way of formulating the Jones polynomial. Now, equivariant mirror symmetry explains his peculiar construction. Why do you treat the caps and the caps differently? Now, this way of rephrasing the A model, which a priori studies maps from two-dimensional domains to the target Y, which is some very high dimensional space, symmetric products of D copies of the Riemann surface. In terms of counting of holomorphic curves in D times the Riemann surface with a pair of projections, one to D as a D full cover and one to the Riemann surface A as a domain with boundaries on one-dimensional Lagrangians, is known as cylindrical approach to Floer theory, and it was developed in the context of Hager-Floer theory. So we are borrowing from it. So in this example corresponding to the right-handed Hopf link, there'd be 8 intersection points and 6 domains that can, in principle, contribute non-trivially to the differential. And so it could give you a complex like this. The cohomology of that complex, together with the 3 remaining points, is the covenant homology of the right-handed Hopf link. And the fact that the differential squares to 0 comes from contributions to Q square canceling in pairs coming from broken maps, which are boundaries of moduli of Maslov index 2 disks with equivariant degree 0. Now, the dimensions of vector spaces in the complex, or the spaces of perturbative ground states, grow in this case always, well, they grow polynomially with the number of crossings in the knot or link, which should be compared with a growth which is always exponential in Covenant's case. So the cylindrical approach to Floer theory brought us reducing of the problem of counting holomorphic maps from D to Y to a well-defined but hard problem in complex analysis, one for each domain on the Riemann surface. Surprisingly, this problem can be solved. The solution of the discounting problem is to make, essentially makes homological mirror symmetry that relates the small x and the small y manifest, and their derived categories manifest. Now, working with the derived Fukaya-Seidel category as opposed to simply with Fukaya-Seidel category is actually simpler. For one, the derived category has far fewer objects, because any deformation of branes that doesn't change the amplitudes is an equivalence. That doesn't change the homes is an equivalence. So by contrast, in Fukaya-Seidel category, you only need, you only get as symmetries Hamiltonian isotopies of individual branes. What this buys for you is that one can generate the whole category by a finite set of branes. And as that finite set, we can take the symbols of the potential W. Now, to every critical point of the potential W, one gets to associate a pair of symbols, a left and a right symbol, which are respectively the set of all initial conditions for either upward or downward gradient flows of real part of W on which imaginary part of W is constant. The critical point equations in our case are a variant of Bethe-Ansatz equation of a Godin model with an irregular singularity. The critical points are isolated and non-degenerate, and they're labeled by weights in the weight space that the conformal blocks transform in. This set of symbols depend on the chamber in equivariant parameter space. They also depend on the chamber in of the positions of associated parameters they come from positions of vertex operators that are complex structure moduli of Y. That's the dependence we definitely want to describe knots. But there's this additional dependence on the chamber in equivariant parameter space. Parameters related to Q or to these extra lambdas. By the way, Q is the variable is related to kappa and the W naught. It's what gives you the variable Q of the knot invariant. The lambdas are associated since we are equipped with the theory immediately describes knots in R2 times S1. Lambdas are associated with holonomies of the transimus gauge field around the S1. Anyway, there's a choice of chamber in this equivariant parameter space, as suggested by mirror symmetry, in which the left symbols are simply products of D real-line Lagrangians. So they are just they're branes that are run along the cylinder, okay, and products of them. These branes are mirrored to vector bundles on X. To formulate the Holmes between such branes, one needs to do a little more work because the branes are non-compact. After the deformation, the intersection points become isolated. There are still infinitely many of them because they model humps between vector bundles on X. Now, the symbols generate an algebra, and not just, which is the algebra of morphisms between them, or spaces of supersymmetric ground states between this direct sum of all the symbols. You get an algebra and not just a vector space because you inherit the product from Floer theory. Now, the remarkable thing that happens is that all the algebra elements turn out to have cohomological degree 0. The fact that the cohomological degree of every element of the algebra is 0 means that the action of the differential is necessarily trivial. Now, the fact that algebra elements are all have degree 0, cohomological degree, mass of or Fermi number 0, is a reflection of mirror symmetry, which maps these symbols to a collection of tilting vector bundles on X. And so anyhow, the algebra you get is an ordinary associative algebra, not some DG algebra, that's graded just by equivariant degrees. Now, there are not many holomorphic discounts that you can evaluate explicitly without an enormous amount of work. But it turns out that all the ones that can contribute to the algebra products are actually computable because they come from products of triangles, which are essentially determined entirely by the D equals to 1 theory. And the computation is actually very similar to what people have done in the Heger-Floer setting. Now, the symbols generates the category of A-branes, and everything there is to know about the symbols is contained in this algebra A. So what we get is equivalence of derived categories of the category of A-branes and the category of modules of this algebra A, the derived category of modules of the algebra A. The algebra the algebras in our story can always be thought of as simply path algebras of a quiver, whose nodes correspond to critical points of the potential, and where paths from one node to another encode the homes between them. For us, these quivers always have closed loops, in contrast to simpler theories where coming from single valued potentials. So this results in richer representation theory and a richer derived category. But what this says is that the category of A-branes is simply the category of modules of quiver representations, as in our very favorite examples of categories of branes on the conifolds, or C3 mod Z3 and so forth, just like that. Now, in fact, for Y, which is the equivariant mirror of the A-1 surface, the algebra is the path algebra of a familiar quiver, just a affine AN quiver, with somewhat unfamiliar relations, which capture all the thimble intersection points and the relations between them. The more familiar quiver with the more familiar relations would arise from B-type branes on the A-1 surface, the big X, where one has this equivalence of the category of B branes with modules of the representations of quiver representations, which is familiar to all. And imposing this funny relation corresponds to restricting the big X to the small x, whose category of A branes is the category of modules of the path of the quiver with these relations. Turns out this relation is exactly a restriction from the big X to its core, this funny long sausage. So in this way, homological mirror symmetry becomes manifest. Okay, it's manifest that the category of B branes on the small x is the category of A branes on the small y, because they're both category of modules of the same quiver. Derived category of modules of the same quiver. So now, this path algebra, the algebra is, as I said, computable explicitly. It has flavors of the algebras that appear in works of Kovanov, Lauda, Roquier, and which Webster generalized. But the algebra and the description of how you get link invariants from it is far simpler than anything known in the literature so far. But the virtue of this derived equivalence of category of A branes with modules of this algebra is that any A brane has what's called a projective resolution as a complex, every term of which is a direct sum of symbols. The maps encode a prescription for how to obtain a brane, any brane, starting with direct sum of symbols and gluing them by so gluing corresponds to giving expectation values to tachyons at the intersections of branes of symbols, and deforms the differential away from the trivial. On the symbols differential, it's trivial. So for example, for Y, which is equivariant mirror of the A-1 surface, the figure 8 brane that serves as a cap has the following resolution with 3 terms, where the maps describe are a precise prescription how to glue the branes, how to glue the symbols to get a figure 8. Now, what's particularly helpful is that the derived category has a second description in terms of the right symbols. So in fact, we get a pair of equivalences, one describing A branes either as complexes of the left symbols, these are real line Lagrangians, or the right symbols. Okay. The right symbols all turn out to be compact on the Riemann surface, and they're dual to the left. This implies that the algebras of endomorphisms of the right symbols, the I branes, is which we'll call A check is related to A by Koszul duality, which is an algebraic way to understand this derived equivalence and has many other important algebraic consequences. Now, the one part of this is important for us today is that among all the right symbol branes are the branes that serve as caps. And that has a striking consequence. It means that we get a second purely classical description of not homology groups, which we can read off from the description of the brane as a bound set of symbols without any further work. Now, as for all branes, the description of the cap branes as bound set of symbols is obtained by starting with the direct sum of symbol branes and deforming the differential by binding branes by elements of the algebra. Now, from such a complex, it's an elementary fact that you get for free a complex of vector spaces. From description of a brane as a complex, you get for free a complex of vector spaces which describe the homes between the brane you start with and any other brane, okay? With an action of the differential this way to 0. For the other brane, we want to take the branes that correspond to caps, the specific I branes or specific right symbols that correspond to caps. The space of ground states and the link homology is simply the cohomology of this complex. So the simplification here is that the terms that appear here are just vector spaces. You don't get some complex of complexes, they're just vector spaces. Now, per construction, the vector space at the kth term in the complex is spanned by the intersection point of equivariant degree J and fermion number K. So the vector spaces are isomorphic to the Floer complex, with the action of the differential that's constructed classically from the geometry of the brane, which solves all the instanton counting problems at once. So you get not just the intersection points of branes, you get also the action of the differential on them, which avoids counting instantons. So this is how this derived equivalence, in fact, the pair of them, solves a not categorification problem. The algebra, I'm badly over time, but let me, actually, maybe I should stop because I am badly over time. I'm so sorry. I did not notice that and nobody complained.
Yeah, if you need a couple of more minutes to wrap up. Okay.
Well, okay, so yeah, so the algebra the algebra that describes the theory is best represented graphically. It's a path algebra of a quiver, but the best way of thinking about it is graphic. So for general G, the algebra looks as follows. So you start with a cylinder. The circle direction of whose is related to the circle in the Riemann surface. And the direction along the cylinder is the space direction of the Landau-Gisbrook model. So on the cylinder, you attach red strands that are colored by highest weights of the representations that are at the punctures of the Riemann surface, or representations that color the strands of the knot you want to study. The algebra elements themselves are configurations of blue strings labeled by positive roots of, by simple positive roots of the Lie algebra, where you can read off the equivariant degrees just by counting the intersection points between the strands or the winding number of strands around the cylinder. The algebra multiplication is simply stacking the cylinders and rescaling. And the relations say that the blue strings need to be taut or the algebra element vanishes. The KRLW algebra of Kovanov, Lauda, Roque, and Webster is given by similar terms, but with more generators and with different relation. By the theorem of Webster describes the category of branes on the Coulomb branch. On the big X, so it's naturally more complicated because the big X has twice the dimension of the spaces we're working. like what happened for the A-1 surface. Now, at the moment, at least, the prescriptions of obtaining link invariants from the scalar double algebra are far more opaque than what I described, possibly because at the time, before my first paper, people lacked the geometric understandings of branes that serve as caps and cups. So maybe that will get improved. So anyway, just to finish off, so for example, for the trefoil, we would get a following configuration of branes. And for simplicity, we can just ask about the reduced covenant homology, where a reduced covenant homology corresponds to setting the unknown homology to be trivial, or normalizing the Jones polynomial, so the expectation value of the unknown is 1. So this lets you erase a pair of Lagrangians, so simplifies the problem to just d equal to 1, and puts us back in this running example. So one of the cap branes has a following resolution, which you can just read off directly as a complex. And out of the complex describing the brane, a small part of it, picked out by which cap brane you want to choose, reproduces the reduced covenant homology of the trefoil. So, okay, thanks for bearing, and I apologize for running so terribly over time.
Thank you very much. Thank you, Mina, for a very interesting talk. So any questions?
Yeah, I have a question. So let's see, you know, Mina, that you can write the Fukaya-Seidel. There's a physics approach to the Fukaya-Seidel category where using the Morse theory. But in that, and you can construct the branes and interfaces, all that. But there it's really important to include the instanton corrections. So towards the end of your talk, you were saying that you had a formulation where you could just use the naive differential without instanton corrections.
It's not a choice for me. In principle,
so
there would be instanton corrections.
I lost so many details that I wasn't sure how relevant it was to the original Fukaya-Seidel category, but one statement is surprising.
It's just a calculation that in this case, the algebra A, the algebra of endomorphisms of symbols, is not a DG algebra or A infinity algebra. It's just an ordinary associative algebra, which follows from a computation, which from an actual calculation. Okay, so the fact that it would have to be a DG algebra in a simple example of say branes on the AM-1 surface or its equivariant mirror, you can see by equivariant mirror symmetry, right? In that the branes on the AM-1 surface are just the derived category of B branes on the AM-1 surface, just the modules of quiver representations, and the differential is trivial there.
Yeah. Okay, I'm probably not following too many details, but I mean, can you give? Are you actually able to give an example of a Fukaya-Seidel, sorry, of a Landau-Ginzburg model, where one can check that there are no instantons?
It's not an example. It's not a general fact at all. If we were to study GL1,
no, but just
if we were to
taking the example,
if we were to study GL1/1 theory, okay, which is a close cousin, the differential is not trivial. You don't get an ordinary algebra. You get a DG algebra.
No, I'm quite sure that in general, I'm just asking if I could take your statement and sort of reverse engineer it and relate it back to a Landau-Ginzburg model and see if, I mean, it could be that to be equivalent to that Landau-Ginzburg model, the instantons would have to be non-zero. But
sorry, so I'm not understanding because the algebra is derived from the Landau-Ginzburg model.
Well, that's okay. That's
what are we trying to reverse engineer?
Well, tell me, what is the Landau-Ginzburg model where the zeta instantons don't make any corrections to the naive differentials?
The Landau-Ginzburg model I described.
Okay, so you claim in that Landau-Ginzburg model there are no corrections
for this specific set of symbols.
Okay.
It's very important to work in a specific chamber. if you between arbitrary pair of branes, of course there are disk instantons.
No,
It's
but
just that between in this specific choice of chamber of equivariant parameters,
but you're not saying if I take into account all thimbles, there would be no instanton corrections.
So it's not all. So which the set of branes that generate the category depends on a choice of chamber in equivariant parameter space, right? So you can choose. There are many other choices one could have made. Okay. What I'm saying is that this is a good one. So for example, suppose you're just studying category of B-type branes. Okay. The fact that the category of B-type branes is the category of modules of representations of some quiver is the case mathematicians love. That case, what they would say about it is that it's a case when the derived category has what's called a tilting generator. Constructions of these tilting generators is a huge problem, which was solved in some cases. It was solved by Bezrukovnikov and Kaledin for big X's, which are holomorphic symplectic, using quantizations in characteristic P. Okay. What this says is that in this, with help of mirror symmetry, you can bypass work in characteristic P and actually get a way of constructing this tilting generator from mirror symmetry. Its existence is not guaranteed by anything on side. In some sense, what's okay? What it is, the reason these theories are really good to study. Okay, if you study branes on the quintic, there's no tilting generator. Okay, the reason this family of examples is really nice from purposes of people who are just interested in mirror symmetry is that they originate from very special deformation of a hyperkähler space by turning on this equivariance, which if you turn it off, the theory would be trivial. Turning it on gives you a theory which is as solvable as you'd want. Okay, so that's sort of hand wavy understanding why this works. Okay, but it's not guaranteed by anything other than this n equals to 4-ness of the underlying story.
Any more questions?
And I could have chosen a different chamber where, so the fact that, you want to find a chamber where some symbols are these real line Lagrangians that run along the cylinder is simply, follows the intuition of the simplest example of mirror symmetry we know, where you can sort of understand it directly what it does on branes. Say, take branes on a cylinder, right? So if you take a brane that runs just in one dimension, one complex dimension, right? So if you want a brane that that's mirrored to a vector bundle, you want a brane that a Lagrangian. This is the real line running along the cylinder. Okay. And even then, even if you have branes that are mirrored to vector bundles, of course, it's not guaranteed that homes between them will always be non-vanishing in cohomological degree 0. Okay, you have to get lucky. So for the theory to actually have tilting generators, and here one's lucky.
Seems like incredibly lucky, actually.
Fortune smiles, but it's not surprising, right? Again, this construction of Bezrukovnikov and Kaledin tells you get an associative algebra, right? Except that actually, from their story, spelling out what's the vector bundle, what's the actual tilting generator is hard. You can construct the algebra, but the geometric input of what it actually comes from is people actually don't have. So I think really the way to solve the theory is mirror symmetry and this Landau-Gisberg model in one dimension. And it's also nice because it puts the host, not just, not invariants associated with ordinary algebras, but also supergroups in the same setting. The Hager-Floer theory and Coulomb homology are now manifestly in the same world, not just, by some mystery. So of course, depending on who you talk to, different things are more surprising.
Okay, so let us thank Mina again, and I will stop the recording, and if anybody has more questions, we can stay and discuss more. Thank you.
Thanks so much. Thanks for listening.